Let's now try to use a second method to derive the same formula that we did over here, but let's focus on the Venn diagram. We want to derive an expression for the number of elements in A union B union C. So that would be the number of elements in at least one of these three sets, which would be given by the number of elements lying within this bounded region enveloping the three sets. For convenience, let me mark the regions in this Venn diagram. This is region 1, this is region 2, this is region 3, this is region 4, this is region 5, this is region 6, and this is region 7. We want to make sure that in the expression that we will be deriving on the right hand side, the elements in each region are counted exactly once. They are not double counted or triple counted or under counted. Here is the same Venn diagram, but instead of numbering the regions 1, 2, 3, 4, 5, 6, 7, I have labeled them A, B, C, D, E, F and G. I've used letters instead of numbers here because we want to count how many times each region will be counted, and so I'll just keep track of those counts within the Venn diagram. So I didn't want those counts to be confused with the names we use for the regions. So our goal is to count the number of elements which appear in A union B union C. Now what's the simplest way in which we could start? We could start by just adding up the number of elements in the three sets individually. So let's add up the number of elements in A, the number of elements in B, and the number of elements in C. Would this give us an accurate count? Well, if the three sets were mutually disjoint like this, then adding the number of elements in each set individually would have given us this value. But there is also an overlap between these three sets. So many of these elements are going to be counted more than once in this sum. So the elements in region A would have been counted once, the elements in region C would have been counted once, and the elements in region G would have been counted once. Why would these three regions have been counted only once? Because they lie in exactly one set. This region lies only in set A, this region lies only in set B, this region lies only in set C. So the elements in these regions would have been counted only once in this sum. But if we look at regions D, B and F, the elements in region D would have been counted two times. Once when we were adding the number of elements in A, and another time when we were adding the number of elements in C, because this region is common to A and C. So it would have been counted two times in this sum. It would have been counted over here and it would have been counted over here. Similarly, region B would have been counted in N of A, and it would have been counted again when we added N of B. And region F also would have been counted once for set C and another time when we were adding the number of elements in set B. What about region E over here? Region E belongs to all three of these sets. So region E would have been counted three times. It would have appeared in this, it would have appeared in this, it would have appeared in this. The elements would have been counted three times. So since we have double counted these three regions and we have triple counted this region, we need to subtract these elements out from this count. So let's focus on one of these regions. Let's say we focus on region D. How do we subtract out the elements in region D? Well, one thing we could do is we could subtract out the elements in A intersection C. We could subtract out the elements in A intersection C. That would reduce this count to 1 and it would reduce this count to 2. At the end, our goal is to have a count of 1 in every region because we want the elements in every region to have been counted exactly once. So one way to start rectifying this scenario is to subtract out the number of elements in A intersection C. By doing that, we would be reducing this count to 1. So in the resulting expression, the elements in D would have been counted only once. They would have been double counted over here, but then they would have been subtracted out over here once. So we would have them being represented only once in the resulting expression. Likewise, the elements in region E were counted 3 times, and by subtracting this term out, now they would have been counted 2 times. So let me erase this count 2 and make it 1, and let me make this count as 2. Now let's come to region B. The elements in region B are being double counted. So let's subtract out the set A intersection B. That will reduce the count of this region to 1, and it will reduce the count of this region to also 1. So we subtract out the set A intersection B, and by doing so we would be reducing these two counts to 1. Now we have region F left, which is being double counted. So let's subtract out this set B intersection C, which will bring down the count of this region to 1. But along with bringing down this count to 1, it will bring down the count of the elements here to 0. So that's also a problem, because we do want these elements to be counted once. So how do we add back exactly this region E? Well, the region E can be expressed as the intersection of A, B and C, because this region is common to all the three sets. So we can add it back in by adding the number of elements in A intersection B intersection C. So by doing so, by adding them back in, we would be now increasing their count to 1. And now finally, every region has been counted exactly once in the formula that we have over here. And you can see that this is the same formula that we derived above. We can rearrange these terms. This will be n of A plus n of B plus n of C minus the number of elements in A intersection B minus the number of elements in B intersection C minus the number of elements in C intersection A, that's this term, plus the number of elements in A intersection B intersection C. So we can derive the same formula just by looking at the Venn diagram. And the way we did that was by ensuring that we start with a basic skeleton formula, and then we try to bring down the counts of all these regions to exactly 1, so that at the end each region is being counted exactly once in the resulting formula.